Good morning. My name is Molly Kembrick, and I want to thank you all for joining us today for our webinar. Before we jump in, I would like to give you a brief introduction to TriLogic and what we do. For over 30 years, TriLogic has provided software and services enabling engineering groups to design, develop, and deliver products through excellent support, training, and consulting services to help you achieve success sooner. Oasis Sales has been a mentor, premier partner for over 16 years. Their industry knowledge and experience make them uniquely qualified to understand your business and how technology will make their customers successful. As you can see, highlighted here on the map are the regions that each Oasis and TriLogic cover. Here you can see the different design and product management areas that TriLogic covers. You'll notice that we have tried to create a suite of products that will provide a front-to-back solution all the way from concept to end of life. And now just a couple of housekeeping items. You can open and close your control panel with the small arrow at the top on the left. There are two ways to join the audio. You can either join with your microphone speakers or your telephone. The instructions, if you wish to switch, are in the audio section of the control panel. Today's presentation is being recorded and should be available within 48 hours. All participants will be in listen-only mode during the presentation. Please submit questions via the question panel in the GoToWebinar control panel. And now I would like to introduce our presenter today, Walter Goody. Walter has over 25 years of experience in ASIC and FPGA design and holds an MS in electrical engineering from Washington University in St. Louis. He worked for over 6 years doing ASIC design at Tel Labs operations. From there, he went to work for Mentor Consulting, where he consulted on various ASIC projects, including time spent in München, Germany, and Helsinki, Finland. For the last decade, Walter has worked as an application engineer supporting Mentor's line of functional verification products. Please welcome Walter.
Thank you. As I said, I'm Walter Goody. I'm an applications engineering manager at Mentor Graphics, and today's topic is on safety critical design, and then we're going to touch on how we can help you accomplish your safety critical design goals using a few of our tools. So first of all, I'll just go over a little bit of a safety critical design overview. Then I'll talk about how to do requirements tracing with our Req Tracer tool, talk about coverage closure, making sure and proving that you've tested everything. And then the last section, we'll talk about a tool called SecureCheck, which is about making sure that you don't have paths that malicious hackers can exploit. So first, just for safety critical design, some of the issues that we end up seeing, and this can be actually within any design, you can see a lot of these issues. Not going to go through them all, but we'll talk about an ad hoc process versus a structured process. So, generally an ad hoc process, you haven't really planned things out really well. The work is just kind of being done. There's not a lot of metrics to document what was done. You couldn't necessarily repeat it if you had to. And then in the case of a safety critical situation where you have some kind of a auditor who's looking at it, it's hard to describe to them what you did and describe, how you've made sure that the goals were worked. So in a structured process, we're looking at something where we've done a lot of planning up front. You're focusing on the requirements and requirements tracking. You're using repeatable processes. You're documenting everything along the way. And it's much easier than to show that you've done this. And I apologize for the graphic here. We're trying to say that you do a lot of verification up front while you're doing the implementation and hopefully shorten your lab time. So a structured process is really all about design and assurance. We really want to look at some of the best practices we've found in the industry. We've kind of based a lot of this work in the past. It was focusing on the DO-254, the civil aviation standard, but now we're seeing in the automotive world, the ISO 26262 and medical standards and the banking standards, and we're seeing this need for a structured process become much more widespread and have a lot of different applications in a lot of different industries. So safety critical design flow, this is something that, again, was pretty much developed during the last decade or so, and it's similar to what you'll see in the DO-254 world, but this applies to most safety critical design. And the first part is really kind of the critical part, is doing a lot of the planning up front, creating process documents, creating requirements documents that are traceable, doing maybe some conceptual design, high-level design, and then the design part of it is a fairly normal RTL flow, but you do hook it back into that requirements tracing, and then the verification side of things is doing your normal simulation, maybe directed type flows. Code coverage becomes very critical, clock domain crossing analysis, and then some of the other things, maybe using assertions, some security analysis, gate level timing simulation, and then actual device level simulations, and correlating the results between each of those stages. So the first thing we'll talk about is the requirement and the planning documents. So planning up front is critical. You know, I mean, this is kind of maybe obvious, but, you know, if you're going to build a house, you don't want to just start banging walls together. You need a good set of blueprints on how to get there. And that's essentially what these design documents in the FPGA and ASIC world are about, is creating the plans that you're going to use first and then following those plans. So what goes into a good FPGA design plan? First of all, you need to provide the context. You need like a system overview of what the FPGA is going to fit into, some context for that FPGA, some related plans for the board and the other things. You need to document the team who's going to be on it, what their responsibilities are, give an overview of the hardware and the functions, talk about the life cycle of the whole design, and then lay out a schedule, including all the reviews and potential audits that you're going to do. So the next few slides I'll go through fairly quickly. It's just giving kind of an example of what I'd say is a good shell of a design script. So, you know, our planning document here, obviously you give the title of the design that you're talking about, maybe a part number, some overview. You want to have some kind of revision control notes in there. So you want to give it a unique ID and kind of a revision. You probably want to have a sign-off page of all the people who have to approve. So you list all the interested parties and the sign-off on the document. You certainly want to have a revision history within the document. You want to have a table of contents in that document. And then a few of the sections up front that you want to have is basically, you definitely want to have this purpose and scope that clarifies what this document is, just in a couple of paragraphs so somebody can pick it up and know for sure what this is, and then list the team members and their roles. The next thing here is just kind of a high-level overview of the architecture of the FPGA, laying that out, and then maybe some stuff on how the design is going to be done and what the review process is for the design section is going to be, and then a similar thing for what is the verification methodologies we're going to do. So how are we going to verify the RTL? What tools are we going to use? how are we going to verify at the gate level, how are we going to verify at the system level, and then list any tools that we're looking at. And then the final slide I'll show here is just if you have any kind of a certification process you have to go through, you want to detail that towards the front of this document again. So you want to talk about what the certification process is, who the certification liaison is going to be, and etc. So from that point, then the document starts to go into the requirements phase. It is describing the requirements and describing how those requirements are going to be implemented and how those requirements are going to be tested. And so that all kind of comes down to requirements and then the tracing of the implementation and the testing of those requirements. So a classic way of doing requirements is called the V process. And that's where we start kind of at a high level, maybe at the system level, lay the requirements out there. You do some design, some conceptual design, show that you've met all those, and then slowly you break down those documents into more and more and more detailed design until we get down to, in this case, the FPGA. So we're kind of showing going from system level down through the hardware part of it, down to subsystem level, maybe a board level, an FPGA. And then the idea is that you're doing verification of each of those stages, and then you're showing how that is correlated at each stage. So it's kind of going down the one side, and then coming back up with validation. So you're doing validation of that, and then validation that that meets here. And it really comes down to this idea of setting requirements at each level and showing how those are traced. And so requirements tracing is all about capturing requirements, reviewing those requirements correct, managing those requirements, making sure you don't lose track of them, making sure that they're well documented and well enumerated, and then tracing the requirements down through your, first of all, usually your document hierarchy, then tracing down into the design and the verification, and showing that traceability across that whole thing. So what is a requirement? A requirement describes a objective or solves a problem, or but it's really a concise description of that. It is a specification of what you should be implementing. It is a description of system behavior or property, and it's really the knowledge and expectations that we need, and then the trick is how to get that knowledge into writing and get that knowledge implemented in your FPGA. So an effective requirement should have these things. It should be complete, correct. It should be implementable. It should be unique. You need to put priority on it. It should be clear, traceable, all kinds of things. So let's look at a requirement. So kind of the diagram of a requirement is that every requirement should have a unique requirement ID. This requirement ID should never be duplicated within the project that you're working on, and potentially should never be duplicated within your company. You should never have different requirements that have the same ID. A good practice is to use the word shall. So if you put that word shall in there, then it forces you to write the requirement in a clear way. So first of all, you have the requirement ID. The requirement text describes the requirement, and it probably wants to use that word shall. And then you may have coverage tags. So where this says that this requirement covers a requirement from a higher level document. So you probably, unless you're at the very top level, are going to have those coverage tags. and then you may have some attributes within that requirement. So the attribute tags are, the things that are saying, okay, this is safety critical, this has a high priority, low priority, priority 1, 2, whatever. So attributes are optional things within a requirement. So here's an example of a very bad requirement. So let's read this. The digital clock converter can be configured to any width or depth, but it will be 250 words deep and support 64K memory with sufficient address and data bits. It will need some kind of reset function. Also be sure to avoid asynchronous clock domain issues between the CPU and the memory interface. And it's got a requirement ID, and then it's got the wrong closing thing. So there's a whole lot of problems with this. Let's look at how we should have done that. We probably should have taken this requirement and broken it down into a bunch of different requirements. Actually, let's start over here with the sins. First of all, we didn't use the word shall, and that sets you up to do bad things. Second of all, there's really 5 requirements lumped into that one requirement. Next, it contains stuff that's not really a requirement or, theory of operation. There's just descriptions of stuff that's not really a requirement. You have to be very specific. So I think in that requirement it said it needed to be fast enough or very fast. That's very confusing. And then it also casts things in a negative light. It said avoid CDC issues, whereas you should say your requirement should be CDC issues should be tested or shall be tested. There shall be no CDC issues, something like that. And then, we have an undefined link tag in there. So let's look at what we should have broken that down to. There shall be an asynchronous reset. The CCC shall support 2 independent clock domains. There shall be a 16-bit address, shall be a 32-bit data. It shall have 256 words of cache for a 64-bit or 64K memory. So you can see, rather than this confusing requirement, we've broken it down into 5 implementable, feasible, clear, et cetera, requirements. So where do you store requirements, and how do you capture them, and how do you trace them? One option is you do it in an Excel spreadsheet or in a Word spreadsheet, and that's kind of what a lot of people in the requirements world refer to as Excel hell, in the sense that when you are trying to trace in an Excel spreadsheet, a lot of the work of doing all that, making sure that you have coverage and tracing becomes a manual process, and it can be very, very difficult. Another option is you can use a requirements capture tool like doors, IBM doors. In the mil-aero world, you'll see that a lot of times they are required to use doors at their system level. The problem with that, well, the good thing about it is a system designed for capturing requirements. It is very good at that job. The problem is it becomes harder and harder to do that as you break down smaller, lower and lower into your system requirements. You cannot put a text document into doors very easily because everything that goes into doors is a requirement. And so at some point you want to be able to write this theory of operation document, but you want to be able to trace that along with your doors document. So your requirements tracing, hopefully you can trace it through both being in that requirement capture system, but then also into your documentation tools like Word or other things. So really what you're trying to do with requirements tracing is verify that the device is performing its intended function, and then be able to track that, control the requirements, and communicate that to the stakeholders who are your customer, your boss, and any certification body that is involved in the project. So how do we trace documents, and how can we create this tracing, and how can we ease the ability? So I have this requirement. I want to show where it is implemented in source code. Maybe I want to trace what it covers from a higher level document. I also maybe want to trace it down into how I test that requirement. So I trace it down into my test bench code and show that my test bench passed. And the way that Mentor handles this is we use a tool called ReqTracer. That is kind of the center of our requirements tracing world. And what it allows you to do is to integrate with an existing doors database. So if you are in the mil-aero world and they're saying your high-level system requirements need to be in doors, ReqTracer can hook up to doors. And then once you get to the point where you're writing a spec, you're writing that spec in Word or FrameMaker, or you get a PDF document that has that spec in there, ReqTracer is able to analyze that text document, find the cover directive, reach back into doors, make sure that it has linkage back into that doors database. It will analyze all of your RTL code, whether it's Verilog, VHDL, C, C++. We do have integrations with our other EDA tools at Mentor. So if you're doing board design and you're using DX Designer, you can place requirement tags in your schematics and your constraint editor system. Our synthesis tool reports will create reports that are place those requirements tags that can be processed by ReqTracer. Third-party tools like MATLAB and other tools also do this. So any output logs from your simulations, as long as they're ASCII, you can attach those to ReqTracer, and you use regular expressions to analyze those output logs to find requirements tags. And then if you're using ModelSim and Questa as your simulation database, we can look into that simulation database to find things like code coverage, how much code coverage do we have? And then if you're using assertions or cover points or cover directives, we can attach to those as well and use that binary database as a basis on whether or not we have fully covered our system. And then all of that from ReqTracer, those are all the inputs to ReqTracer. And then what it will output is, do requirements tracing. It'll make sure that all requirements are fully documented and traced and implemented and tested in your system. So you'll get a graphical view of that. You get coverage reports out of ReqTracer, and you get traceability matrices, etc. So we work very closely with some DO254 auditors, some designated engineering representatives, to get the functionality that they thought was needed when they were going in to audit a project. So that was kind of our first basis, and now we've been working a little bit with some of the ISO 262 people to make sure that we continue to keep ReqTracer relevant for the new and emerging standards. So let's look at capturing a requirement. I already kind of said this. Every requirement must have an identifier. So you're going to want to have a unique string that completely uniquely identifies this requirement. You're definitely going to have a description, which is the shall part of your requirements. And those two things are required. And then you may have some attributes. So priority, high, medium, low, must have the highs, lows are optional. And then you're probably going to have a reference, which is a reflection back to a higher level document in the document hierarchy. So we can extract these from many of the enterprise level requirements tools. We can trace through any type of a text document or a Word document or a lot of our binary databases. So let's look at, you know, a simple example here is we have a product requirement at the high level. So this is the high level system requirement, and then we have a design specification for an FPGA. And we'll see that we've put in cover tags on 3 of these documents here, and they're referring back to requirements from the higher level. But this is one thing you will see is that sometimes a requirement at this higher level might take 2 lower level requirements to get fully covered. And so you can have a many to one relationship, or you can actually have this requirement right here actually fulfills more than one of these higher level, so you can have a one-to-many relationship as well. But basically what we see here is if we look at this, it would say that our product requirements are currently only 40% covered by our design specification. So we need to continue to create more requirements with either within this design specification, or maybe it's another specification that is for a different FPGA or for software or something. But at some point in this project, we need to say that every one of these requirements is covered. Now we'll look at this guy and we'll say, okay, we've implemented some RTL code. So we have implementation tags that are referring back from different blocks of our RTL code that are saying that, you know, we've implemented this requirement, we've implemented this guy, we've implemented this guy. So we are still at this point, we only have 60% of these requirements implemented, so we have some more design work to do. And then the last thing that you can do is that you can look at and you can go, this block right here, it is not covering any requirement. What is this block doing? So, you know, that's also some of the analysis that you can end up doing once you have this kind of traceability. You probably also want to have some sort of change management system in place. So within ReqTracer, there is the ability to create snapshots of your design, label them, and then compare one snapshot to another to see what has changed. So in this case, I had this requirement that I showed before, and I've created an alpha snapshot of the design. Now, at some point down the design, I've been working on the design. Some requirements have changed a little bit. You know, the requirements document has gotten updated, and I can say, okay, what's different about today versus that Apple snapshot that I took? And the tool will go back and will flag any requirements that are different between the alpha and the beta snapshot. So in this case, it called out that in requirements 2, I've gone from a high priority to a critical requirement, and I've also added another coverage tag that said, you know, this goes back to my high level thing, and it also is dealing with this requirement tag from the higher level. So this helps to automate some of the communication between the team, and it also helps to make sure that I'm notified when there's been changes, and I know I better go make sure that now design spec 2 has changed. I gotta go make sure that anything that is affected by that downstream is updated to reflect these new issues. And in this case, I can monitor, make sure that things stay on track. Impact analysis is, hey, I've changed this high-level requirement. What does that impact downstream? What requirements do I now have to go update here to reflect this change? And then those requirements, how do they impact my implementation? And then ReqTracer will create all kinds of customized reporting. So you can get Basically, traceability matrices are the things that show the traceability between any one level within my design down to any other level. It shows the full traceability. So this is just showing a one-level traceability matrix, but this traceability matrix could go down 2, 3, 4, 5 levels. So the summary is that ReqTracer is kind of the center of our requirements tracing solution. If you face any kind of a certification body on any of your projects, or even if it's just within your company, you have a stricter design critical flow, being able to look at the impact analysis, the traceability, and create traceability and document and all the artifacts that you need. And like I say, especially if you are dealing with any kind of a compliance with a safety standard, generating those documents can be super important. So the next section we'll talk about is when I'm doing my testing, one of the things that I need to show in a safety critical design is that I have tested all of my code. And code coverage is sort of the tool within ModelSim and Questa that allows me to show that coverage. How much have I done? And so it's really all about making sure that I have exercised my design completely is what code coverage is. So there are many different types of coverage. Line coverage is just, have I executed every executable line? Branch coverage, have I taken true false branch in all of my if statements? Have I taken all the branches in my case statements? And so really code coverage is kind of an umbrella term for all these different types of coverage, but it's something that without changing anything in your design flow, you can just turn on code coverage, run your simulation, and you can identify areas that you have not tested. And if you know anything, Murphy's Law says the one mistake in my design is going to be in the 10 lines of code that I haven't tested. So that's what code coverage helps you to identify. It is built into pretty much any commercial simulator. ModelSim, Questa, or any of our rivals have some kind of code coverage. So statement coverage is just for every executable line of code, it will let me know that like this one I have executed 192 times, this line of code I have not executed. So I need to go back and write some stimulus that'll get my code to execute that branch. Branch coverage is looking at a case statement and it's just saying, you could probably infer this out of statement coverage because I've never taken this branch, so I've probably never covered this line of code, but it's just another step in that full coverage analysis. Then we start to get into some of the more complex coverages, like conditional coverage. So in conditional coverage would be if A or B, then branch true, else branch false. If A and B are both 0, I'll branch false. But if A is true and B is 0, I'll branch true, so I'll get branch coverage at that point. But maybe I've never branched because B was true and A was false. And there's a reason that I've coded that in my code. I want that, so conditional coverage pushes down one level and says, okay, I'm going to look at all the ways I can branch true and make sure I've covered them. Finite state machine coverage. Again, finite state machine coverage is probably something that I can infer from branch and case and conditional coverage. But the good thing about finite state machine coverage is if I have a finite state machine in my design, it will show me that as a bubble diagram. It will highlight, I don't know if you can see on your screen, I have never hit the control state. I've never taken either of these two branches. I've hit this WT word 1 state, but every time I hit it, I've branched this way. I've never branched back to idle. from there. And I've coded that, so I expect that at some point I should do that. So again, I need to write more stimulus until I can get this particular branch in my finite state machine covered. Toggle coverage is something that people debate a little bit. That is all the signals in your design and whether they toggled 1 and 0. There is debate on whether or not you need to do toggle coverage. Probably most standards don't really force you to do that, but it is there if you decide to do it. So now the question is, I've done this, and I've got, let's say I've got 20,000 lines of code in my design, and I have 98% code coverage. Is that good enough? And this is kind of a little joke of, you know, is 98% code coverage good enough? If 98% of your roof is covered and it starts to rain, is that good enough? If you have any coverage holes in a safety critical design, you are required to give a reason for those non-coverages. So you need to create waivers. And there could be legitimate reasons for those waivers. Maybe, you know, you're using RTL code that is a piece of IP, and in the system that you're using it, you have an input tied off, and so you're never going to hit those lines of code. If that is the case, you need to document all the reasons for any of those waivers. And so the challenge in the verification management world can be, you know, what's been covered, what do I need to cover, how long is it going to be before we're done, how can I improve on my process. These are all the things that keep verification, or excuse me, project managers up at night and make them concerned. And so there are different types of coverage, but code coverage is really, you know, the first step in that coverage. And it is what I call a last mile problem. It is really easy to get to 80% code coverage. It's pretty easy to get to 90% code coverage. It starts to get hard to get to 95. It's a lot harder to get to 98. It's super hard to get to 99. And it can be nearly impossible to get to 100% coverage. And sometimes when it's deep, deep, deep down in your design, there are lines of code that are extremely hard to write stimulus to get them covered, or maybe there's reasons that they will never be hit that can be masked. And so the question is, how do you easily get to those parts of the design that are hard to reach, that are buried down, and are those even coverable? So if you are writing directed test benches where you're, you know, creating the RTL code, which I guess most of you are, that can be very challenging in the, you know, how do I get this, you know, one line of code that's buried deep, deep, deep in the design to get covered? How do I get some state machine to do something? Or if you're doing constrained random, you can just keep throwing tests at it, and maybe someday you'll get that coverage. And it can lead to a lot of time and a lot of effort and a lot of uncertainty about whether or not these things are coverable. So traditionally what you would do is you'd have your test bench, whether that test bench is directed tests or constrained random, UVM, doesn't matter. You run your test bench, you get this, Mentor writes out what's called a unified coverage database, and that's basically just where all the code coverage information is stored. And then you have to look at all the uncovered items, and you either have to decide that that is uncoverable and I'm going to create a waiver and I'm going to create the reason why, or you have to say, no, I think that item is coverable and I'm going to write a bunch more tests and I'm going to rerun my simulation and see if that thing gets covered the next time around. Making this decision, is this coverable or uncoverable, sometimes that's hard to know whether or not something is coverable. So then after you've made that decision that it is coverable, then you need to go write those tests. When you get to, 99.5% coverage, you can spend ungodly amounts of time trying to write the test to cover that last line of code. So what Mentor has is we have a tool called CoverCheck. And what CoverCheck does is the flow is the same. You start with your test bench, you run your code, and then instead of you manually reviewing all the coverage holes, you turn it over to CoverCheck. You say, here's the design, here are the uncovered objects, and then CoverCheck uses Mentor's formal state space analysis engine that basically goes through and it starts from reset and it figures out every state that the design can get into, and it turns that state space analysis engine towards the problem of, can I cover this line of code? And it will either come back with a proof that says this line is uncoverable and here's the reason. This line is uncoverable because this state machine will never do this because this input is tied off, or this input is, affected by something else within the system, and it will create that waiver that will exclude that line of code from your database, and it will give you a reason to put into your result. Or if it discovers that that line of code is coverable, instead of you having to write those tests, it will actually create a waveform for you that says, if you put this stimulus, and it shows you the stimulus, you put that onto your design, that will cause that line to be covered. And so instead of spending weeks in this loop of manually discovering and trying to write new tests, you get an immediate result of either that line of code is uncoverable, or here is the stimulus that you would need to cover that line of code. That's really I think that's what I just described, is that CoverCheck will go through the results of CoverCheck. You get to look at all the uncovered lines. It will either give you, this is coverable, and give you the database, or this is uncoverable for this reason, and it'll create the coverage exclusions for you. So it finds all the unreachable code so that you don't waste time. Anyway, so it'll do this for all the different types of coverage, including the functional coverage from System Verilog. So it's not just for code coverage, and it will help you generate all that. So here's an ROI from one customer that said they had 3,000 unreachable lines of code, and they said it would take about 15 minutes to analyze each one of those. So if you're looking at 3,000 lines of code, 15 minutes each, it was about 750 hours of time that CoverCheck, resolved all those 3,000 lines in about 2 or 3 hours. So there's an ROI statement. So the last section we'll talk about SecureCheck. And SecureCheck is all about making sure that your device is, or at least trying to make sure that your device is unhackable. These days we have all kinds of issues with security, with self-driving cars, or even just cars that are on the network. You don't want somebody to be able to hack your car, throttle on your car, so you end up in a ditch. You don't want your mobile wallet on your device hacked so that someone can start charging on you. The cartoon here is that, with the Internet of Things, everything being on the internet, do you want to have to pay a bribe to get your Roomba to clean the house? Do you want to have to pay a bribe to get your trash can to open, or your coffee maker to make you coffee, or whatever else? So we see this all over the place. And then other places that you might need to worry about is maybe not even malicious, but you don't want to have mistakes where in the middle of takeoff, the flaps can come up and the brakes can come on an airplane. So you want to make sure, you know, that it's maybe not even malicious, but that there's just not mistakes sneak past in your design. So the root of that trust begins at the hardware level. You know, I mean, there's a lot of opportunities for hacking, but if you lock down the hardware, you're going to close down more and more of those paths at the higher levels in your design. So, you know, we need to start this analysis at the root. So let's say I have this, in this system, I have this encryption engine. And the encryption engine has a path that has some key storage. And so as far as I know, the only person who should have access to these encryption keys is the encryption engine. So what I don't want to have is that there's actually some snake paths that come through maybe my Axibus or maybe my Ethernet or something from my controller that allows me to sneak in and either see those keys so that I can, you know, have the encryption key and do things, or go in and change the encryption keys and lock me out. And so what we're talking about is either confidentiality or integrity. So there's a lot of paths, a lot of methods that people use to do this, whether it is security by obscurity, means, you know, this is so obscure nobody's ever going to hack my Roomba, or white hat hacking, where we hire hackers to try to do it, or some expert inspection, and then you can just use the regular verification methods. What we really need is something that's mathematical and exhaustive. So again, we're going to turn that formal state space analysis engine to this problem of seeing if there's any snake paths, any backdoor paths into the secure areas of my device. And basically that is just, we have a app called SecureCheck, and what it does is it says, okay, I have identified that these are my protected areas. I have identified the paths that I believe exist there, and then SecureCheck uses its formal state space analysis to try to find counterexamples, to try to find any backdoor paths. And it will do that analysis, and, you know, the desired example or the desired result is that it says, you know, I have proved there are no backdoor paths to those secure things. The undesirable but good to know is, hey, I've identified these paths. You might want to take some action to close those backdoor paths. And then, you know, what you don't want is the unknown of, well, I think that I don't have any backdoor paths, but I don't have anything that's giving me that analysis. And so that's really what SecureCheck is doing. Here's our case study. This was an electronic entertainment system. They used to do a lot of manual inspection. They didn't know whether or not there were some insecure paths, and they used SecureCheck and verified that the secure paths were there. They actually had found some insecure paths through field testing, and so they had applied this to a device that they knew had some, and SecureCheck actually pretty immediately found those paths. And so now they are applying this to all new devices going forward. So SecureCheck is all about having confidence in the integrity of your secure items, making sure that there are no sneak paths for undesired actions to happen, like the jet engine misfiring in the middle of a takeoff, or inspecting that there are no compromising situations to secure data within your system. I'm going to end at this point and look at any questions that might have come in. So let me pull up the question panel and see if there have been any questions. Okay, I have one question. Is are CoverCheck and SecureCheck included with Questa? And no, they are separate formal verification apps. We use the term Questa CoverCheck, Questa SecureCheck. Questa has really become a brand for all of our verification tools. So these are separate add-on tools that are targeted at specific problems. Let's see, any other questions that had come in? Is Req Tracer required by a DO254 or a DO254 project? It is not a requirement to have something like Req Tracer. You can pass one of these security audits without something, a tool like Req Tracer, but when it ends up, you do a lot of manual requirements tracing and documenting. And what we've had customers tell us is that instead of spending, 3 man-months on their requirements tracing, if they were doing it within Req Tracer, it was more like a couple of man-weeks rather than 3 man-months. Has Req Tracer an automation APIs like a Python interface? I think that that's something I'm going to have to take offline. I'm not sure. The way Req Tracer works, and I didn't really demonstrate this, is that for all of the text documents, you set up regular expression search strings within Req Tracer. And so then it goes and processes the text documents, and it looks for the requirement ID strings, and then it grabs all the text around that. I know we have all kinds of coupling notes with different tools. I am not sure if we have a Python API. So with that, I think I will turn it back over to Cheryl. I don't know if you have any last words.
No, I just want to thank you very much, for Walter, and thank everyone for attending today. And we look forward to seeing you at our next webinar.
All right, thanks everyone.